All right. Good morning. How's everyone doing?
Good. How are you doing, Dr. Chrysler?
Doing fine. Last day of August already. Hard to believe.
Yeah, it's going by too quick.
Yeah. I'm trying to remember. It was with last year, if we started a week earlier or last fall semester was kind of weird because it like ended at the before Thanksgiving or the week after Thanksgiving break, but it feels
So, are they doing that same thing this year where they do like we have a week off and then we're doing everything online for as far as finals again, or are we actually in person?
I have not seen anything that says that. And they have not indicated anything that will happen, but I feel like it's kind of hard to say right now.
Okay.
Yeah.
I,
I don't, yeah, I know they don't want to. And like compared with a lot of other universities, Idaho State is fairly like what you can do in terms of, going to campus, taking, classes in person, no social distancing, I think is pretty like that's more than what I think a lot of universities are allowing. But I think they also, because it's the health science university for the state of Idaho, they will likely, take more. I don't know. They'll want to be perceived as, you know, following whatever procedures they can. So I don't.
right.
Yeah. Yeah, so I'm not really sure. I think for this class, the only thing that would change is like what the final situation might be, because previously when they like shut the things down, I don't think they shut down. I think they shut down the testing center as well, which is where you would be taking the final, like in the testing center of whichever campus. So that's the only thing I know of that would be affected for this particular class. Do you just out of curiosity, do you all prefer what like taking these lectures online or in person?
Um, I I like it. I like the fact that everybody has started recording all their lectures because sometimes I miss something in lecture and then I can go back and watch it. But I
Yeah.
definitely think that something's missing from the online as far as in person goes.
Yeah, that's sort of what I feel, but then on some of the classes that I've hold where there is like a classroom option, like this one, I just chose to put it in Zoom only. But some of the other ones where there's an in-person classroom option, just no one would show up to the classroom ever. So then I just figured, well, people must prefer not taking the lecture um, in person. Okay. All right. Well, looks like it's 8 a.m. So let's get going. A couple things before we start that I wanted to point out. All right, let's take a look at the Moodle page. Show you what it looks like as a student. But, right, so hopefully you've all seen, if you want to look at the class recording, I am uploading them to YouTube into a playlist that you can access from here. So feel free to go there. So just like we were just speaking about, sometimes it's useful to go back and review what was said. You can find those here. Do be aware, I'm the one who's actually posting these onto YouTube. So you can see right that on the Zoom screen, you should be able to see it's being recorded. So once it's done, I'm the one who's actually, moving that recording onto YouTube. So in case you don't see it up there right away or something, feel free to send me an email saying, hey, can you upload the YouTube video? Because, there's always a chance that I may, forget or not do it right away. I try to do it right after class though. So just so you know about that. I added another link on here. So this is a link to the textbook website, which we will be using occasionally. So especially for these modules. So in the homework 2, I'm going to have you use one of the modules. So please be aware that this is both on the homework, there's a link, and also on our Moodle page, there's a link to this textbook website, which has some useful information. When you try to run the modules, there are instructions here to, in order to configure Java for your machine. I am using this from a MacBook. I don't know if anyone else is, but you should follow the directions carefully in order to make sure that you can get these to run. It did take me a minute to get it configured correctly, but all of the directions are here. And when I run this, I did need to run it from it helped for some reason to use Mozilla Firefox instead of Chrome. So just follow the instructions when we get there in the homework 2. I also wanted to point out, I have on these, on each homework assignment, right, I have the videos listed here and the date that you should watch them by. So for example, right, this one says, please watch the videos by today. So hopefully you have done that. If not, just be aware for the future that this, I have written next to the videos what date you should watch them before. So coming into lecture, what day you should watch them before. All right. And then the last thing, this is important, right? Please take this practice quiz. You'll get some extra points for the extra credit points for the homework. I think I have it. Yeah, I have it due as on the 2nd, but basically, right, this practice quiz is an untimed version of what the normal quizzes will be like for the class. So just take the practice quiz. All you do is open this up, and get a piece of notebook paper or a piece of paper, write your answers to the questions on it, take a photo, and upload your PDF here to this practice quiz submission. So do this by Thursday. The reason I have it set due by Thursday is because the quiz 1 will be on Thursday. And so you can see this week, right? So you're all tracking. The homework 1 you will submit here this Thursday. Submit it before 8 a.m. for credit. At 7:55 a.m. the quiz 1 will open to you, so you can view the quiz and take the quiz, take a photo of it, convert it to a PDF, and upload it here, just like you did on the practice quiz. And we'll start class at 8:20. So once you're finished with the quiz, the class will start. So those are the kind of agenda items that I wanted to mention. Does anyone have any questions about any of this? So I'll try to remember at the end of class, but just remember, take the quiz. The quiz is what's going to happen at the beginning of our normal class period on Thursday. So plan to take the quiz, and then once you're finished with the quiz, you can pop onto our Zoom meeting, and we'll get class started right around 8:20 a.m. most likely. So, all right. So let us do some homework then. I think we're almost done. Oh, I guess one more item. We're almost done with the homework 1. We're quite close. There is a number of review problems, as you can see. So I think today we'll probably finish homework 1, hopefully start homework 2. And we hopefully we'll get into electrostatics on Thursday, but If not, we'll see. But basically, these homeworks are all kind of spaced out, so you'll have some extra time to complete them if needed. All right, and this is what is available on the Moodle page on the schedule, so you can keep track of what's going on. Okay. All right, so I think last week we looked at these all we thought were pretty straightforward. We looked at this problem and these two. So what problem would you like to look at next?
We'll just look at the 5A real quick.
Yeah, let's look at 5A. All right. So going to 5A. Got the question here. All right, so we have a vector field in cylindrical coordinates. And it's located on the surface of the cylinder. So we have a cylinder described by the radius r equals 2. So I guess first, see if you can take a minute and try to draw this, okay? Draw a cylinder with the radius 2 and determine where is this point P on the cylinder. So on your notebook paper, take a shot at this. Try setting up the problem, by drawing a cylinder and figuring out where that point is located. All right, so we have a cylinder, right? We could say it's infinitely long. This distance, right, is r equals 2. So it has a radius of 2. The point P, so this is what? This is r phi z, right? So this point P, we have some point P that we're given, and where is this? So the r is the radius of the point. So in this coordinate system, in the cylindrical coordinate system, if we look at this point, right, we can see that the point is at a radius of 2. So that's somewhere on the surface of the cylinder. The angle is pi. Okay. And the height is z. So this is on the surface of the cylinder somewhere at a height of z is equal to 3. So that's why. Okay. All right. So we have that point here. So it's basically we could say on the surface here. This is where our point is. All right, so the questions that we want to know are, what is the vector component of E that's perpendicular to the cylinder, and the vector component of E that's tangential to the cylinder? So not only do we have this cylinder that's in this space, we also have some field, right? So this is a field, right, E, and it's a vector field. How do we know this? Well, right, it is vector. It has vector components to it, and it is a vector. So we call it a vector field E. So this vector field E is comprised of magnitudes in the cardinal directions for this coordinate system, r, phi, and z. And so we could look in our space that we have, and we could find any point in this space, and we could figure out what the vector field is in this space, right? So this vector field is described, I'm sure we can see all of it, like this, right? And so we could plug in values, right, for r, phi, and z. We could plug in any values for r, phi, and z, and we could come up with an expression that says what the value of the vector field is at a point, right? So just like we could have a scalar field, we could also have a vector field, and we could have choose a point in space that we could evaluate the field at. So in this case, we want to find the vector component of E. And we want to break it down into the perpendicular and tangential parts. All right. So when we're on the surface of that cylinder, what is perpendicular to that cylinder? Which one of those vector components is perpendicular to the cylinder?
R.
Yeah, and how do you know that, or what what makes you say that? How do you know it?
Because he is on the surface, on the outside surface of the cylinder, so perpendicular to that surface would be in that R direction.
Yeah, so so the R is the correct answer. So the vector component that's perpendicular is the R component. It's that radial component, and it's perpendicular. And sometimes we also call that normal. So perpendicular or normal, they could be used interchangeably here. All right. So what is another way to think about this? Well, if we're on the surface of this cylinder, okay, so the surface of the cylinder is here, right? And if we move around on the surface of the cylinder, what changes? So we have R, phi, or z. So when we move around on the surface of this cylinder, what is changing? Is R changing?
No, R doesn't change. It's only phi and z that change.
Yeah, only phi and z change, right? These are the ones that change. So this is another way to look at this. R is not changing, so that must mean that it is perpendicular. Phi and z are changing. So what do you think that says about the vector components that are tangential? Do the tangential components change? Yes, no? Yeah, the tangential components do change, right? So when you're on the surface and you're moving around, the tangential components are the ones that are going to be changing. So the vector component of E that's tangential will be phi hat and z hat. All right, so if knowing this, take a minute now and see if you can find the vector component that's perpendicular. So we know now which direction is perpendicular. So which part of this field is perpendicular, and then evaluate it at this point. So on your piece of paper, determine which part of this vector field is perpendicular, and then evaluate it at this point.
Quick question.
Yeah.
First question. So since our pi is our angle is pi, does that affect where we place the cylinder?
Does that affect
where the cylinder is placed? Because where you drew the cylinder right now, is that pi or should that be pi over 2?
Oh, that is a good point. Yeah. So how could we check that? Let's check that. That's a good question. Okay. So let's check that for one, and then also, will it matter for this problem? I don't think so, but let's check it. So we have oh yeah, I actually drew this incorrectly here. So we have this cylindrical coordinate system, right? It looks like this. So I just pulled that off of that vector cookbook, which again, I recommend that you do print out if you can. All right. So more accurately, what I should have drawn the cylinder like this. And then we take the angle from X, right? So here, what is phi equal to when we're on this X-axis?
Pi.
Okay, so if we take the angle starting from here, what is the phi here? Is it pi?
0.
Yeah, it should be 0, right? And then here, pi halves, and then all the way over here should be pi. So I guess it's a little hard to see, but that point should be basically here. We could draw it like this. How about this? This will make it easy to see. Z equals 3, z equals 0. So our point is right here. So we've gone all the way around to phi equals pi. Thank you. Good question. I did. You are correct. This should have been that. All right. Okay, so now that you have this and you can see it exactly, find the vector components of the of this here. Right. can still see it if it's too small, but find the vector component that's perpendicular and the vector component that's tangential at this point. So try that on your piece of paper now. And once you've finished the perpendicular part, go on to the tangential part. And then if you've got that finished, upload it to the Google Drive. Take a picture and upload it. All right, so I'm seeing one in there. All right. Okay, can you all see this work now? All right. Daniel, would you like to explain how you did this?
Based on the explanation you gave earlier on about R being the perpendicular direction to E. So I chose the R vector, the vector in R direction, and I substituted the values for point P in that direction, gave the answer I got. Then the same thing for the tangential. Since phi and z are the ones changing, so I used the vectors in their direction and substituted values for p at that point.
All right. Does everyone agree with this answer? What do you think? Yes, no, get something else?
For both these perpendicular and tangential, we do have to plug in the points once we do the dot product or whatever.
Yes, and yes, yeah, do plug in the points. Yes, yeah. Although we are not actually taking the dot product, because the dot product would give us a scalar result. And these field components will still have a direction associated with them. So the perpendicular component is directional. It is perpendicular to that cylinder. And so we'll want to take note of that. And we take note of that by using vector notation. Likewise with the tangential components. So let's see. Let's see who else hasn't spoken yet. Is this all making sense? AK, you got this? Did you get the same answer?
Yeah, I'm just trying to figure out how to upload it because I don't see the classroom in my Google Drive somehow. I was
Okay.
trying to upload I guess the solution, but I got the same answers. So
Okay, perfect. Gabriel, are you good on this? Does that make sense?
Yeah.
Okay, you got the same answers.
Yeah.
All right. AK, I think you may not have been added to this drive, so you can check now. I just sent you a link, so you should have access to this one now. Yeah. Mario, are you good? Are you here with us? Not today. Cade, you got it? This all seeming good to you?
yeah,
Yeah,
I'm checking right now.
Okay. All right. Okay, so before we go on, let's look at this for one more second. Not this problem, but just a related one. I want to point this out because this idea of perpendicular and tangential comes up a lot in electromagnetics or whenever you're dealing with fields. And it's hard to say like the exact reason why, but it often has to do like with the mathematical components that you come up with, right? So if you remember, if we took A cross B, right, this is going to give us this result is actually normal, right? Or perpendicular to the surface that A cross B is on, or that A and B create. So this is one reason why this idea of normal and perpendicular comes up a lot, is when we're performing these mathematical operations, we're going to get results that are normal to surfaces that are created by vector fields. And then the same, right, if we take A dot with B, right, that won't be perpendicular to that surface. It would be on the surface. So the mathematical functions that we end up using frequently result in the creation of different vector components that are normal or tangential. And so this idea is important to think about, because as we deal more with like electromagnetic structures, that determining what is normal or tangential comes up. So let's look at something too real quick. I'm just going to draw a cube. And let's consider this surface. So what is normal to this surface? We have X, Y, or Z. What is normal?
I
Yeah, Y is normal, right? So it's in this same direction. And what is tangential? It's the other two, right? Is the X, Z. Now, what about this surface on the top? What's normal?
Z component.
Yeah, so the Z component, right, is perpendicular to this top surface, and that is the normal direction. And the tangent is would be XY. Okay. And we could do this for all different types of things, right? If we had like a half, if we did it in another coordinate system, right, we could have a half a sphere. I don't know, kind of hard to draw. But we could determine the tangent and normal components of these, right? So if we look here, so make sure we get use the coordinate system the correct way. But right, when we're using this coordinate system, if we have a sphere like this, and we would measure the phi angle here, the theta angle from here, and then the R angle outwards. So on this surface, this face surface, if this is like half a sphere, what is the normal to this?
DBR.
Okay, so on the face, if I move around on this face, so let's imagine this is, we've cut like a ball in half. We've cut a ball in half, and this is the flat part. So if I move around on this, what's changing? If I move all around on this surface, does R change? Yeah, R is changing, right? Because I could go from here to here. That's a change in R. So R changes. What about phi? Does phi change as I move around on this face? So the phi, we're on this flat face. It's kind of hard to visualize this the way I've drawn it quickly, but we're on this flat face. If the angle phi, or it's flat, so if I'm measuring the angle phi, I don't think phi is changing. But what about if I go from here to here, is on this surface, is theta changing? So if I move from this point down to this point, did theta change? Yeah, theta does change. Yeah. So this one has no change. So which one is normal?
Your phi is going to be the normal.
Yeah, so this one, in this case, is normal. Okay, so the normal one, if you have a surface and you move around on it, the directional component that does not change would be the one that's normal to that surface. So R and theta would comprise the tangential component. If we were on this other area, like out here, if on the back part of the sphere, so if this is a ball that's cut in half, we could see that in that case, right, R is not changing, right, on the surface of that sphere that's cut in half. So R would be the tangent to that other part. Right, so if we're over here on the other half of this is like the ball, right? R is not changing, so sorry. Okay. All right, so not a homework problem, but an important thing to note. Now, let's take a look. So any questions on that problem?
I just still don't get how we decide what is normal and not on the square.
What is normal on this one? So the general method for all of this is take a surface and look at the surface and then imagine moving around on the surface. So in this case, we have this surface, this red surface. I can imagine moving around on this red surface. When I move around on the red surface, the X, we can change in X and we can change in Z, but we never change in Y on the red surface. So based on that knowledge, we can determine that this has a normal component of Y hat. This is also made a little bit simpler because this cube is like the basic, each surface of this cube is comprised of a component in that coordinate system, right? So if we had you are correct that if we had something else like a surface that was like half this cube, I don't know if we could somehow draw a triangle that three-dimensional, right? This surface, this would have a more complex normal, right? This normal would be, when we move around on that surface, right, this normal would be changing in all of the directions. So this would be a more complex normal. But when we do a cube in Cartesian, a cylinder and cylindrical, or a sphere and spherical coordinates, which are the most common things to do. The normal and the tangent will be comprised of just the vector components that create that coordinate system. Sorry, did that make things more clear or less clear?
Yeah, it gave me an idea. I think I just have to look up more like examples.
Yeah. So throughout this class, in the way that I like to think about it, a lot of these things, when we're doing surface integrals, finding normals, finding tangents, taking dot products, doing cross products, I really like this method of looking at a surface, imagining in your mind moving around on the surface, and that will tell you things like which direction the derivative goes, right? Like if you're moving around on the surface, you can determine which parts of the derivative to use, or the normal, or the tangent. So I'm just trying to set the stage basically for ways of thinking about the surfaces and structures that are inside of coordinate systems. Okay, any more questions? Let's look at one of these real quick. All right, so determine the distance between the following pairs of points. So which one of these do you want to try? A, B, or C?
Can we do C?
Yeah, let's do C. Oops. So we have 2 points, P5 and P6, and we want to find the distance between those 2 points. All right. What coordinate system do you think this is in?
Sphere.
Yeah, it looks like it's spherical. All right, so take a moment on your piece of paper. See if you can find the distance between these pieces of points, these 2 points. If you need to, right, pull up your vector cookbook, see if there's anything in there that could help. And then see if you can find the distance between those 2 points.
So do you want this uploaded as well?
Do I want the what?
The C part uploaded.
Yeah, if you have it finished, upload that and we'll take a look at it. All right. So Calvin, do you want to explain your method here?
Yeah, I can. So that first part, so it's basically what's in the vector cookbook. It shows you how to find the distance between, the points, and it gives you a formula for it. So basically you take the radius portion and add those, square both of them and add them together, and that's where you get the 25 from. 9 plus 16 is 25. And then you subtract 2 times the radiuses, and then you also have the angles in there. But all of these angles, since they're at pi and pi over 2, whenever you take cosine or sine of either one of those, it goes to 0. So that whole entire second term ends up negating itself, and it just ends up being the square root of 5.
Yeah, so yeah, basically, yeah, you're saying this part, oops, not this part. This part ends up being equal to 0.
Yeah,
Yeah.
and that second part does too.
Okay. Yeah, that second part does too. All right, and then you also said that you got the formula from the cookbook. So if you go to the cookbook, right, and if you scroll down to the second page, you can see there's the distance, some formulas for distance between 2 points for each different coordinate system, right? So this, you said, okay, this is spherical. And this one is spherical. All right, so which one would you use for this? Part B. Which one of these formulas?
So, the second one.
Yeah, so use this one for the cylindrical. And this one for the Cartesian. All right, great. So I think should be able to wrap up this homework 1 fairly easily. So let's open up homework 2 now. If you go onto the Moodle page, you can find homework 2 if you haven't looked at it already. I'll pull it up here also. So homework 2. Let's see here. Got right here. So we have some questions on vector algebra. So these are using transformation relationships. Okay. Then we have some that go on to vector calculus. So finding for scalar fields, do some calculations, right? So find the gradient, find the divergence, and then for these ones, you are finding the cross product and the dot product of these. So the you're performing all of the vector calculus operations. There's one question on Stokes' theorem, and then Laplacian, and then the last one is about using one of these modules. Okay. All right, so these ones are most related to the section we just did. So use the cookbook, take a look at the cookbook to do these. Let's start in on some of these vector calculus ones today. Get some practice doing this. All right. So we're given a bunch of scalar fields here, and we want to obtain the analytical solution, right, of this. This is the analytical solution, right? This is del T, right? So when we take this, what does it tell us when we perform this operation? What is this operation describing? What could you say this operation is doing? Oops, you aren't seeing that at all, are you? One moment. When you perform this operation, what is the operation and what does it describe?
I want to say that is, isn't that the divergence that you're trying to find? And that shows like how, I want to say how quickly the field is changing in that area.
Yeah, so the first part was a little off. This is actually the gradient, but the second part was totally correct. This does describe how rapidly the field is changing in that area. So from that, we can find how rapidly the field is changing in a certain direction. So this one, all right. So this is, oops, the gradient. And the gradient takes a scalar field. And what is the output? Is it scalar or vector?
Scalar.
Yeah, did I hear vector? No, you heard scalar? Why do you think it's scalar? So we put a scalar in, so just maybe we get a scalar out. Is that what you're thinking?
Yeah.
Okay. All right. So actually for this operation, the output is a vector. So it takes a scalar in, vector out. And like Calvin said, this describes how quickly a scalar field is changing. And what were some examples of scalar fields that we discussed in, I think maybe the first day? What's an example of a scalar field?
meters.
Yeah, so if you have a meters or a set of distances, I think my example was temperature, right? So maybe you have a, right, if you have something really hot, so let's say that you have a heating element. Okay, if you have a heating element here, you could then write a field, right? You could define for this whole area, right, temperature, right? You could make a scalar field, temperature, right, where temperature is a function of X and Y, right? And do you think the heating would be, just intuitively, would the temperature change more quickly closer to the heating element or further away from the heating element?
Closer to it.
Yeah, so this is a perfect example of why we might want to find the gradient, right? You might want to know how quickly the temperature is changing when you get closer to some kind of heating element. In our class, right, we're going to be dealing with electromagnetics. So we might want to know how quickly something like the voltage is changing, right? So this is, the voltage is a, right, that would describe, voltage is a scalar. So that would describe how quickly the potential is changing when you're getting near a charge source. And we'll talk more about that later, but this, so del T, this is the gradient. It takes a scalar in, gives a vector out, and it describes how quickly a scalar field is changing. All right, so on the Moodle page, you can look in that calculus cookbook, and we have a whole set of these, right? So we have the gradient, the divergence, the curl, and the Laplacian down here. So we want to do perform this gradient operator. So we look in each direction, each coordinate direction, and see how quickly a field is changing in that direction. And the overall result tells us how quickly that scalar field is changing. All right, so see if you can compute this result now. So for A, see if you can compute A, and then try drawing a arrow representation of this. So first compute this. And then 2, draw the field.
So I have a quick question.
Yeah, go ahead.
The restraints on X, is that just, is that actually
The what on X?
the restraints like -10 to 10?
Oh yeah, that's this part is for the drawing. Just
Oh, okay.
there to draw. Yeah.
I was starting to get confused. Okay, thanks.
Yeah. All right, so what is the partial derivative of t with respect to x? So if I take the partial derivative of this with respect to x, what is the result that I'm going to get?
You'll just get 1, right?
Yep. Yeah. So if I take the derivative of this, that's 0. If I take the derivative of this, that's 1 when I take it with respect to x. All right. Now, if I take the partial derivative of t, so just to be clear, right, this is d dx of 10 plus x, right? This is 0, and this goes to just 1. All right. Now for this one, if I take dy with of this, so the derivative of 10 with respect to y, that's also 0. What about, oops, this should be x. And the derivative of x with respect to y, right, that's also 0. So this is 0. And then what about in the z direction?
That will also be 0.
Yeah, that one's also going to be 0, right? Because we're taking the derivative with respect to z. There's nothing that's z valued here, so we also end up with 0. So the gradient of this is just x hat or x hat 1. Now, if you wanted to draw the vector field, okay, let's think about the vector field that we want to draw. So the vector field is just in the x direction with a magnitude of 1 wherever we are, right? So if I'm here, it's in the x direction with a magnitude of 1. If I'm here, x direction, magnitude of 1. If I go below here, right, it should be x direction, magnitude of 1, x direction, magnitude of 1. In this quadrant, x direction, magnitude of 1. If I go here and evaluate, right, the field is still in the x direction with magnitude of 1. So no matter where I draw the field, right, it's in the x direction with a magnitude of 1, right? This does not change, right? There's no variables that you could plug in. So no matter where you are in space, right, this gradient is not changing. So it has, what could you say about the slope of this? It's like a constant slope, right? It's not changing more quickly anywhere. Okay. All right. Any questions on this one? So the rest are, they're a little bit trickier, but not much more. The arrow representation is on all of these is going to be just like we did in the homework one, where we drew the arrow representation for that problem. Okay. Don't know if we'll have time to finish this problem, but let's look at the next one. Okay, so this one is asking us about divergence. So divergence is this operator. So what is the input to divergence, and so is the input scalar or vector on when we calculate divergence? And what is the output?
Is that gonna be the input vectors and the output scalars?
So output scalar, input vector. Let's take a look. So we have, as an example, right, we have some vector we can see because it's a vector. And when we take we can see that this does not have any of the directional vectors in here, so that is correct. Thank you, AK. Right, we have inputs are vectors and outputs are scalars for the divergence. What is the meaning of divergence? So if you had a vector field, let's say it's a electric field, okay. So if you have an electric field and there's a point that has a divergence that is not zero, what does that say about the electric field at that point?
Say that one more time.
So if you have a field, let's say it's an electric field, and there's some point that is not equal to, and if you have an electric field and you take the divergence of it, and you have some point where the divergence is not equal to zero. So it's you have some value. You take the divergence and it's more than one or less than one. Take the divergence of an electric field and it's more than one or less than one. What does that say about the field at that point?
Doesn't that just mean how much it's changing from the normal? Like, I mean, yeah. So how much it changes from the average?
So this is not describing the way let's see. I'm trying to think if you might be onto something. I think it's more, I'm not exactly sure. Let me say what I think a good way to think of this is and see if this is what you're getting at, Calvin. But if you take that divergence and it's non-zero, that means that there's either a source of a field or a like sink for the field at that point. So there's, if you take the divergence, you have a field and you take the divergence of it. So you input your vector field. So like you input an electric field vector, you take the divergence and you get an output that's a scalar. And that will tell you something about the field at that point. If it's not zero, it will say that there's either a source of charge there or a sink of charge there. And if it's zero, that means that there's nothing generating that charge. So this is something that we'll think about a lot in this class, but we have things like charges, which create fields. And then we look at them using calculus to say something about it, whether it's like a source of charge or a sink of charge, or if there's no charge there. So this result, meaning, so when we look, we are often interested in determining if the divergence of a field is divergenceless, which means it's equal to zero, because that means there's no source or sink of the charge at that location. This is going to come up. We'll do these computations later, but divergence is an important one to think about because this tells us about the relationship between the field and the location of things that create the field. So there's two relationships that we're going to look at later. One is the divergence of the electric field, right? And this one can be non-zero, right? Because what creates electric fields? charges exist, right? So electrons exist. What about magnetic fields? Can this be, if you take the divergence of a magnetic field, can it be non-zero? Can you find a source of a magnetic field? Is there a magnetic particle?
No,
Yeah.
magnetic fields come from the switching.
Yep. So this one must be zero. We get the magnetic field from other things moving. These are two really important equations to Maxwell's equations, but we'll think about divergence a lot in the future, and this can be thought about as a relationship between a charge and the field that it creates. And so we're often interested in this because this tells us something about whether what is happening at a point. Sometimes I think, well, class is basically over, but another way to think of this, right, is fluids have all these same things, right? If you have a like velocity field of on your fluid, and you have a non-zero divergence, that means that somehow the fluid is getting compressed in one location or getting expanded in one location. It's either a source or a sink of your fluid particles. So that might be another physical interpretation that you could use to help you understand this, that might be a little more familiar. Okay, so we're done here. Next Thursday, make sure to take that quiz. It'll open at 7:55 a.m. If something's going wrong, send me an email. I'll be sitting at my computer looking at the emails, making sure that everything's going okay. But take that quiz right away. Take the practice quiz before Thursday. You'll get some extra credit on the homework, and it'll be good practice to make sure you know how to take the quiz. If you have any questions about the class, stick around for a few minutes and we can chat about it. And if not, I'll see you at 8:20 on Thursday.
Professor, I have a question for the
Sure.
homework. I went back to the previous lectures. I haven't seen my number. I was wondering how to do that, or
Okay, yeah, you can just submit your homework onto Moodle, and you don't need a number. Yeah. So yeah, and this time we'll just do everything online. So I'll be
Okay.
up.
Gotcha. Thank you.
Yep. Anything else?